there's the title of the talk. I'm going to explain what all these different things are and show you some really nice pictures taken by satellites. So these are the satellites that have been funding me, and a large part of that $15 million that he was talking about has come from NASA to my group over the past, I guess it's 15 years now, to explain to the public, people like yourselves, and also to school children, what these satellites are doing up there and what they're looking at. So these are the 4 different satellites that have mostly been funding us. The first one is named XMM Newton. I won't tell you or show you much from that satellite. It's actually a part European satellite, so it's NASA plus the European Space Agency. And it takes pictures in low energy X-rays. We call those soft X-rays. I will show you a bunch of stuff from the SWIFT satellite that was launched in 2004. It's looking for gamma ray bursts. I'll show you a bunch of stuff from Fermi, used to be known as GLAST. That was launched in 2008. That looks at the sky in the very highest energy gamma rays. And then I'll show you some stuff from NuSTAR, which is our newest satellite, just launched a couple years ago. And that images harder X-rays, more energetic X-rays. Okay, so what are X-rays and gamma rays, and what are we actually observing? This graph shows all of the different kinds of light that exist in the universe. We call that the electromagnetic spectrum. It goes from the lowest energy stuff, shown on the left, radio waves. As you increase in energy, you go through microwaves, infrared. Right in the middle is visible light, the kind of light that we see with our eyes. And as you keep going to higher energies, you get to ultraviolet, and then X-rays, and finally the highest energy light of all, gamma rays. So these square boxes in different colors show you the different wavelength bands of the 4 satellites that I was just telling you about. You see Fermi all the way up at the far right. That has the highest energy light. And SWIFT actually has a ultraviolet optical telescope on it, so it's going all the way down to the visible. And then XMM is the green one with the lower energy X-rays, and NuSTAR has the higher energy X-rays. To put it in numerical terms, the energy of the light that we see with our eyes is usually about 1 or 2 electron volts. That's just a unit. It's how much energy it takes to take an electron and put it through 1 volt. X-rays start at thousands of electron volts. So the lowest energy X-rays are 1,000 electron volts. We call that kilo electron volts, KeV. Gamma rays start at millions of electron volts, MeV, all the way up to billions of electron volts, GeV, giga electron volts. So when we're looking at the universe with X-rays or gamma rays, we're seeing light that's thousands to millions to billions of times more energy for each little light ray than the kind of light that we see with our eyes. And what we see are very different visions of the universe. When we look with X-rays, this is just a little thing that shows the electromagnetic spectrum again and shows where the X-rays are. We mostly are looking at very, very hot gas, objects that have temperatures of millions of degrees. And the gas is glowing, and that glowing gas makes the X-rays that we see. Things that glow that are millions of degrees are things like supernova remnants, which is the gas left over after the star explodes, and the disks of gas that are orbiting black holes. Because as the gas moves in towards the black hole, it gets hotter and hotter until eventually it gets to millions of degrees and makes the X-rays that we see. So now I'm going to show you a little movie. This is NuSTAR. So this is our newest satellite that was launched 2 years ago. It's in orbit around the Earth, just like all the other satellites that I'm going to show you. And NuSTAR is very unusual because it was a cheap little satellite, and it had to be launched in a rocket. It didn't get launched from the space station. and it had to be all folded up in the rocket when it was launched, and here it is shown in its folded up configuration. About a week after it was launched, it extended the detectors and separated them from the telescope with this mast that is 10 meters long, so about 30 feet long, 33 feet long. It took 24 minutes to do that. The principal investigator of the satellite, Fiona Harrison from Caltech, calls this her 24 minutes of terror because this kind of thing is not usually done in space before. But you can't focus the X-rays, especially not these high energy X-rays, without having the detectors separated from the telescope by this distance of about 10 meters. So, NuSTAR is a very unusual satellite and it's working really well. Okay, this is what a larger X-ray satellite looks like. This is XMM Newton, and it looks a lot like the Chandra X-ray Observatory, if you've ever heard of that one. And it also has a similar energy range, about 1 to 10,000 electron volts. And the telescopes, you can see the green circles there, just looking out at space, and the detectors are at the other end. But it's also about 10 meters long. It's just that it was a very expensive satellite, and it got to be launched all in one piece. Okay, so what about gamma rays? Now we're moving up in energy by about a factor of 1,000. And so you might imagine that if gas that's 1,000,000 degrees makes X-rays, then gas that's 1,000,000,000 degrees might make gamma rays. The problem is there isn't very much gas out there that's actually 1,000,000,000 degrees. Maybe at the very second when a star explodes, there can be 1,000,000,000-degree gas, but that's really pretty hot even for the universe. So most of the gamma rays that we see are made by charged particles that are being accelerated by really, really strong magnetic fields or really, really strong gravitational fields. You see the strong gravitational fields around black holes. So this is a picture of SWIFT. This is a gamma ray burst mission. It has 3 different telescopes on it. One looks for bursts, one images ultraviolet and optical. It has an X-ray telescope, and it's called SWIFT, not an acronym, named after the bird, because when it sees a big blast of gamma rays coming from somewhere, it swiftly turns around and gets its telescopes pointed at that place on the sky so that it can look at the burst at lower energy wavelengths. And I'll be showing you some of this SWIFT burst later. And then last but not least, here's Fermi. This is my biggest satellite. This is the one that has supported my group the most since 2008. We've been getting data from it now, so it's been up there for 6 years. And it is studying all of these gamma rays from millions to billions of electron volts. But it doesn't look anything like a telescope that you might have seen before. That big square metal box on the top is actually the telescope. And the little things on the side are more things looking for gamma ray bursts, and there's a total of 12 of them. They look in all directions and see all the whole sky at once. So this little movie shows how Fermi images the gamma rays. It can't focus them like the X-ray telescopes I've been talking about. It has these trackers that are made out of 19 layers of alternating silicon strips and lead. And a gamma ray photon comes in and converts into 2 particles, an electron and a positron, and they go all the way down to the bottom, and then we trace where they went back up through all those layers of detectors, and it points to a place on the sky. And so we're actually using Einstein's most famous equation, E = mc squared, as the basis of this telescope. The E is the energy of the gamma ray, the m is the mass of the particles, the electron and its antimatter counterpart, the positron, and the energy of the gamma ray is turned into the mass of the particles. There it goes, it's just converted into particles. And those little glowing X's are the charge tracks that we read out in the detectors to reconstruct the path back to the place on the sky where the gamma ray came from. And so that doesn't make really great pictures. It's not like focusing like the X-ray telescopes can do, where you actually get a pretty nice picture. But it's the best pictures in gamma rays that anyone's ever been able to take. So we're pretty happy with it. And this is what the entire sky looks like when you view it in gamma rays. Now, this is the kind of map I'm going to be showing you a few more of these later. This is the entire sky. The bright band across the middle is the plane of our own galaxy, the Milky Way. And when you look away from that, either above or below, you're looking outside of our galaxy. This is a projection that's sort of like, if you think of the whole sphere of the sky around you, and you unpeeled it like an orange and flattened it out and put it down, this would be like that. This is like the orange peel of a whole, spherical globe. And the place on the far right is actually the same place as the place on the far left, right? So that's how the orange peel works. And right in the very center is the center of our galaxy. So the brighter colors mean more gamma rays, and the darker colors mean fewer gamma rays. And all of those little bright points of light above and below the galaxy are distant galaxies that we can see shining at us in gamma rays. And what we're mostly seeing when we study those distant galaxies are the big black holes in the centers of the galaxies shooting out jets of particles, and these accelerated particles are moving really, really close to the speed of light, and when they accelerate that fast, they make gamma rays. So we call those active galaxies, the ones that have the jets, and we call the ones that point their jets right at us blazars. Now, it's a big mystery. If a black hole is supposed to be sucking in everything that comes too close, how is it that these black holes can shoot out these jets? That's one of the things we're trying to figure out. First, let me show you this video that actually has narration.
Spiral galaxies are collections of dust, gas, and billions of stars forming a flattened disk. But at the very heart of this galaxy lies a monster. Astronomers have discovered that every major galaxy has, at its core, a huge black hole, with millions or even billions of times the mass of our sun. In a normal or quiescent galaxy, this picture is fairly serene. But not all galaxies are quiet. In some, gas and dust are actively falling onto the central black hole. This material forms a flattened disk, called an accretion disk. Friction and other forces heat the disk to millions of degrees, so hot that it emits X-rays. The disk becomes incredibly bright, outshining all the rest of the galaxy. When this happens, the galaxy is said to be active. Some active galaxies blast out beams of matter and energy, emanating from near the central black hole. These jets are powered by the accretion disk, probably focused by the disk's rotation and magnetic fields. But their ultimate nature is still not well understood by scientists. After traveling outward for hundreds of thousands of light years, the jets slow and finally stop as they ram through the thin gas outside the galaxy. Where they stop, the jets puff up, forming giant clouds of radio wave emitting gas called radio lobes. Astronomers have learned that active galaxies like this one take on very different appearances depending upon the angle to us. If we view the galaxy edge on, from the side, dust in the accretion disk blocks the most energetic light, and the fainter radio lobes are easier to spot. But if the galaxy is tilted with respect to us, the hotter, brighter X-ray emitting material from the inner accretion disk can be seen. The lobes become more difficult to see. A face-on galaxy means we are looking almost straight down the jets. The intensely bright, but relatively small, accretion disk completely outshines the dimmer galaxy, and all we see is a star-like point. This type of galaxy is called a quasar. If the jets are aimed precisely at us, super high energy gamma rays in the jets can be detected. In this extreme case, we call the galaxy a blazar. There are no hints of jets, lobes, or even the galaxy itself. All we can see is a flood of gamma rays from the very core of the galaxy. This one type of object, an active galaxy with a central supermassive black hole, an accretion disk, and jets, can appear very different depending on the angle at which we see it. It is only when we view galaxies in different wavelengths of light, radio, optical, X, and gamma rays, that their true nature becomes apparent.
Okay, so there you have the explanation for what we think we're seeing when we see these blazars. Before Fermi was launched, there were about 5 blazars that were known. So those are the galaxies where the jets are aimed right at us, okay, with black holes in the centers that are millions to billions of times the mass of our sun. This is how many blazars Fermi has found in its first 5 years of surveying the sky. It's about 1,000. Okay, so something that we thought was really very rare turns out to be actually the most ubiquitous source of gamma rays in the universe. It gives us evidence that there are these huge black holes inside of all of these galaxies, some fraction of which have jets, and some fraction of those are pointing right at us, so that we can see this flood of gamma rays coming out. It doesn't answer the question where the jets have come from. In order to do that, you have to study more of the properties of the galaxy. But observations that have been taken of some of the more close-by ones, where we can get a better look, seem to indicate that the black holes that are in the centers of these galaxies are rotating really, really fast. And that rotation wraps up magnetic fields inside the accretion disk and then channels the material perpendicular to the disk and shoots it out. Not everything that goes into that disk falls into the black hole. Sometimes it gets caught up in the magnetic field and shot out at right angles. So the Fermi satellite scans the sky every 3 hours, and we look for flares from these active galaxies, from these blazars. This is an example that shows one day and then the next day, and you see the one on the top gets really, really bright just in one day. So that black hole just had a big dinner. We are trying to figure out exactly what kind of particles are in the jets, what are making the gamma rays, what are making the flares. There are many different models. We don't even know if the charged particles are positive or negative. The different models predict different behavior for the different wavelengths of light. Some of them say the visible light should flare first and the gamma ray should flare later. Some of them say the opposite. Some of them say they should flare at the same time. And so we have been conducting ground-based campaigns with visible light telescopes, coordinating them with our space-based satellite telescopes, and trying to figure this all out. But I don't have a good answer for you. It's definitely a good scientific mystery and a current, emphasis of a lot of research. Now this is an image from XMM Newton plus another European satellite, the Herschel Space Observatory, that looks with infrared and radio light. And this just shows a pretty picture of an active galaxy that's seen more from the side. So now we're getting to see the X-rays, and they're the purple, blue, and cyan colors, and infrared and radio light in yellow and red from a different satellite put together in a composite picture. Moving a little closer to home, here is a galaxy seen in visible light, but NuSTAR looked at it and saw the two objects that are in purple, and they're not in the center of the galaxy. I'm pretty sure this galaxy has a big black hole in the center. You can see it's a very pretty spiral. Everything looks like it's moving around the center. But this galaxy also has some smaller black holes in it, black holes that are only about 1,000 times the mass of our sun, and we call those intermediate mass black holes. If they were heavier, if they were millions of solar masses, they would be in the center. Here's a couple more medium-sized black holes. You can see they're not in the galaxy. There's a little purple one below that sort of funny-looking irregular galaxy, and then there's one that's clearly not in the center. And then here's a galaxy that has a supermassive black hole right in the center, and another smaller one off to the side, and the galaxy on the right. So we see black holes pretty much in every galaxy that we can observe well, in one wavelength of light or another. Now here's our own black hole. This is the black hole at the center of our Milky Way galaxy. This one weighs 4 million times the mass of our sun. And although it's not particularly active, it does have a snack every once in a while. Just a little one, not a big dinner like the one that made the big flare that I showed you before. But NuSTAR was looking at the center of the galaxy, and so there's an infrared view, there's the X-ray image, and then on the right you see like a little time-lapse movie where it was rather dim and then it got bright for about a week and then it dimmed back down again. So our own galaxy does do some interesting stuff every once in a while, but it's really a pretty boring galaxy compared to some of the blazars that are popping off and, you know, making fireworks, you know, on a daily basis or a monthly basis. Okay, next subject, the exploding stars. I'll get back to black holes at the end again. This is all related. So this is the life cycle of different sized stars. They all start off as that sort of mushy red blob in the middle, which is just a bunch of gas. And then gravity draws that gas together and forms a star. It can be a sun-like star if you look at the circle on the left. Our sun will end its life as a red giant once it's done burning all the fuel inside. And then when the red giant is done burning all the fuel in that, it just becomes this very pretty thing called a planetary nebula, which has nothing to do with planets, it's just what astronomers call them. And then it just cools down, the central core cools down, and it just sort of ends its life with a whimper as a white dwarf. On the other hand, if there's enough gas in that star-forming nebula to make a really big star, when it self-gravitates, that really big star will end its life in a supernova. It will explode when it runs out of fuel in the core. And depending on the size of the core that you have left, it will either collapse down to be about the size of a city, in which case we call it a neutron star, or it will collapse all the way down and become a black hole. So it still has the mass of at least 3 times our sun, but it has basically no dimension. It becomes a point-like object. Supernova are a lot of fun to observe. When that explosion occurs, all of the elements that were created in the star throughout its entire life get thrown out into space. And as Carl Sagan used to say, we are the star stuff. That's where all of the heavy elements on Earth came from. That's where the gold in your rings came from, the carbon, the nitrogen, the oxygen. It all came from stars. And it made our way into the Earth and into us by being thrown out into space with these big explosions. This is what a supernova looks like to an astronomer. There's a before picture of a pretty galaxy, and there's an after picture that's got a supernova in it. Can you spot the supernova? It's right there. Okay, so astronomers have to look at galaxies a lot, and they blink pictures, you know, before and after pictures, and they see whether something shows up that wasn't there before. And that's how they discover supernovae. But many tens of thousands to millions of years later, we can look at these remnants of the supernovae, and we can study them and see what kind of light are coming out. And this is the Cassiopeia A supernova as seen by NuSTAR. The highest energy X-rays are in blue, and they were not seen before. And notice they seem to be around the outside of the expanding shell of gas. And the inner parts of the shells show the lower energy X-rays. Those were also seen with the Chandra Observatory. And so when the star explodes, you get this big shock wave that goes out, right? It rams into the surrounding medium. Where that shock occurs is where the highest energy X-rays come from. So it makes sense that this emission that NuSTAR sees, the higher energy X-rays are on the outside. But NuSTAR can go one better. It can actually make an image of the star in radioactive titanium. So this shows you all the places in the supernova remnant that actually contain the element titanium. And the yellow is the non-radioactive material. So by looking at the star in different wavelengths of light with different X-ray telescopes like Chandra and NuSTAR, you can actually see lots of different elements that have been formed in the inside of that star coming out after the explosion. And then sometimes you can even see God. So this famous image is called the hand of God, because it looks like a hand. I don't know if you can see it. It looks like a hand going like that. And it's really just gas that was blown out of a neutron star that was formed in a supernova explosion. But it looks sort of interesting like. The high energy X-rays are in the blue color, and the lower energy X-rays are in green and red, taken from the Chandra Observatory. So this is just one of those, strange looking things that you see out in space when you make enough images. Okay, well, what's more super than a supernova? How do you go beyond a supernova? Well, that is something called a gamma ray burst. And we see two different kinds of gamma ray bursts out there in the universe. The first kind is made from the collapse of a massive star, say 30 times the mass of our sun. It gets to the end of its life, it's run out of fuel in its core, all of the extra material is getting thrown out, and the accretion disk that's around the core ends up collapsing in, and then it makes a big explosion. It hasn't collapsed yet. There we go. There's the explosion. Okay. And so that model is called the collapsar model, or the hypernova model. Astronomers like to hype stuff, so hypernova must be the thing that comes after a supernova. Another possibility is that you have two neutron stars that are going to coalesce. So they're orbiting around each other, and their orbit gets closer and closer, and at the very end they collide and they make one bigger object that's actually a black hole and send out a big burst of energy. So in both cases, you end up with a black hole at the end. So we say that gamma ray bursts are the birth cries of black holes, and we see one gamma ray burst from somewhere in the sky about once a day. So each gamma ray burst is emitting as much energy in just a few seconds as our sun puts out in its entire 10 billion year lifetime. Okay, one of these happens somewhere not too close to us. Haven't been any in our own galaxy, but somewhere in the universe, somewhere in the sky, we see one of these gamma ray bursts every day. This is, the whole sky is seen by Swift. The image in the background is the infrared sky, so you can see where the galaxy is. But these are all the bursts that Swift saw in the first 8 years of its life, color-coded by year. As you can see, they have absolutely nothing to do with the plane of our galaxy. They are not at all located in our galaxy. They are all from different places on the sky. Whatever was there blew up and is never heard from again. They never repeat. You never get two gamma ray bursts in the same place. This is the gamma ray burst seen by Fermi. Now, people didn't think that the Large Area Telescope on Fermi, that highest energy gamma ray telescope, was going to actually see any gamma ray bursts because they were supposed to be too not energetic enough to be seen by that telescope. It could be seen by the gamma ray burst monitor, so there are 1,300 of them as of February of this year, seen in the gamma ray burst monitor. There were 174 of them seen by Swift in the same time period, but there were 73 of them seen at the very, very highest energy gamma rays, and that was quite a shock to everybody. We were not expecting that. That means that the energies that are coming out in the gamma ray bursts are even more than we thought, and we already thought that was, a lot of energy just for a few seconds worth of explosion. This is what a gamma ray burst looks like if you look at it versus time. So this shows the count rate on the vertical and the time on the horizontal, and it just shows lots of big blasts of gamma rays. The one thing about gamma ray bursts is that if you've seen one gamma ray burst, you've seen one gamma ray burst. They all look totally different. And so that's been quite a challenge for the theorists to figure out, to explain how if something's blowing up, it can look so different all the time. Because the supernovae, which are stars blowing up, actually look pretty much the same as each other. Okay, so here's the most recent news that I have for you. The gamma ray bursts are labeled by their dates. And this one happened in 2013 in April, on April 27th. It was the first burst seen that day. This was the shockingly bright gamma ray burst. This is the all-time brightest gamma ray burst that was seen since these satellites were launched. And so on the left you see the sky before the gamma ray burst, and on the right you see how the gamma ray burst totally dominates the entire hemisphere of the gamma ray sky. It also had the highest energy single photon, single light ray, 94 billion electron volts. So 94 billion times as much energy in one photon as what our eyes detect. The burst lasts for about an entire day, so lots of satellites and ground-based telescopes are able to get involved and look at the thing. And all of this energy is coming to us from 3.6 billion light years away. And that's actually a Swift image of just a tenth of a second of data. It saturated the Swift detectors. It was so bright. And so we had this whole flotilla of satellites looking at it. Of course, they weren't as close as the artist's conception on the left. That's Fermi, Swift, NuSTAR, the ground-based telescope, all staring at this thing. And the plot on the right shows all the different results from the different telescopes. Those are the results that go into the models that the theorists then try to figure out exactly what blew up and how that all worked. And why was this burst so bright? So for my last little video here, we'll have the star. We'll zoom into the star. It's still burning all of its nuclear fuel in the center. The big jet of material starts to come out of the center of the star as the star runs out of fuel. And then it keeps going out, and eventually the camera pulls back and shows you there's a jet coming out the other side. And now it's hitting the interstellar medium, so it's ramming into some gas around the star and making a big shock wave. And just like with the active galaxy, if the shock wave, if those jets happen to be aimed right at us, you're going to see a really, really bright burst. And that is what we saw. So there's the Fermi image again of the sky. That was a black hole being born, one of many that we've seen. That one was in 2013. And so, in conclusion, I think I've shown you that the universe as seen in X-rays and gamma rays shows us a very different view of these extreme and exotic events. And only by putting together observations at many different energies, we get a complete picture of our universe. I hope you enjoyed seeing the visions of the high energy universe and the black holes. Here's just some websites from all these different satellites that I've talked about. And you can find them all just by going to my group's main website, and you can also learn about the Rocket Project and all the other different things that we're doing. If you just remember one, just remember the top one. Thank you very much. Okay, time for questions.
Any question?
Please wait for the microphone.
Issue with the discussion of supersymmetry, or SUSY, and Higgs bosons, and I wonder if you might be able to tie into that a little bit without going too far over our heads, and give us some thoughts about what happens if that theory doesn't work out.
Okay, well, this question really has nothing whatsoever to do with anything I've talked about so far. So the gentleman's question was about theories of particle physics. So the things I've been telling you about are these really, really big things out in the universe. What he's asking about are the most infinitesimal little subatomic particles. Okay, so the Higgs boson was recently, there was evidence for the Higgs boson. It was discovered at CERN, which is a particle accelerator in near Geneva, Switzerland. And the Higgs boson is the particle that is believed to give the mass to all the other particles in the universe. Now, how it does that, the Higgs boson is the force carrier for the Higgs field, and you can think of the Higgs field as like a bunch of molasses. And so when the other particles are moving through the Higgs field, if they can move through it quickly, then they're really lightweight particles. And if they move through it really slowly, then they're heavyweight particles. And the strength of their interaction with the Higgs field, their interaction with the field is carried by the Higgs boson. So to explain particle physics is an entirely different lecture. That would take me more than an hour to explain to you. The other thing the gentleman asked about is supersymmetry, Susie, it's known as. So supersymmetry is a version of particle physics beyond the standard model. The standard model, by the way, has the Higgs boson in it, in which every particle that we know and love has a supersymmetric partner. Now, I showed you a little tiny bit of that in what I showed you when we were doing the E equals MC squared with the Fermi detector, because I showed you a gamma ray turning into an electron and a positron, which is its antimatter particle partner of the electron. So a positron is just like an electron, but it has a positive charge, the same mass. So those are the antiparticles that we already know, and we already have measured many properties of these antiparticles. For every particle, there's a proton, there's an antiproton, there's an electron, there's a positron. So all of the normal particles that people have created in particle accelerators have antiparticle partners. What supersymmetry says is there's a whole nother set of partners that have different symmetric properties. Okay, so instead of an electron, you'd have a selectron, because they put little S's in front for supersymmetry. So no one has found any of those particles yet. Doesn't mean they're not looking. They are looking with that particle detector in Switzerland that found the Higgs. But people think that the energies for these supersymmetric particles are very high, and so they're a lot harder to find. Anyway, it's a good question. It has nothing to do with this talk, but it's a very interesting question. No, wait for the microphone.
I gather that what we've been hearing is basic science. Is that correct?
This is very basic science, yes.
Are there any applied science applications derived from
Okay, so are there any applied science applications that can be derived from black holes or jets shooting out of black holes or stars exploding? No, not so much. What we really like to study about black holes are, the reason that I personally like to study them, aside from the fact that I've been a big science fiction fan my whole life, I thought it was really cool that somebody would pay me to do science fiction for a living, because it's actually not fiction. They're actually out there. We get to test the laws of physics in these very extreme conditions. Magnetic fields that are trillions of times the strength of the ones we find on Earth. Those are the kind of fields we see on the pulsars. Gravitational fields that are more than trillions of times the gravitational field on Earth. Those are the kinds of fields that are near the event horizons of black holes. And so we like to know whether the laws of physics and whether Einstein's equations and Einstein's predictions can actually hold up in these very extreme conditions. We know they work on Earth, we know they work for the solar system, we know they work for the galaxy. We know we know that general relativity is a very good theory of gravity, because if it wasn't for general relativity, the GPSs in your phones wouldn't work. If your GPS devices didn't make general relativistic corrections, they would not tell you where you are with any kind of accuracy. So we know that we can test these things in what's called weak field gravity. But why we like to study black holes and these extreme objects is so that we can do these same tests in really, really extreme physical conditions where there might be some other physical law. Except so far, Einstein's always been right. Okay, we'll go to this side of the room.
Do these gamma rays come through our atmosphere and reach us? And if so, what effects do they have on us as humans?
Okay, so we are really, really lucky, and it is sort of ironic that these extremely energetic gamma rays that come billions of light years across the universe get all the way to the Earth and then don't make it through the Earth's atmosphere. They interact with molecules in the atmosphere and they turn into lower energy particles and photons. If they did make it all the way down to the Earth, life would not have formed and we would not be here having this lovely discussion. So we're very happy that they don't make it through, and the X-rays don't make it through either. And so I should have said that at the beginning. That's why we put the detectors on satellites and launched them above the atmosphere to send us down the data. We cannot see the X-ray sources or the gamma ray sources from the ground. We can see visible stars from the ground, right? So that's okay. Although you get a much clearer view if you put the satellite above the atmosphere, which is why the pictures from Hubble are so spectacular. But no, we don't get the X-rays or the gamma rays here on the ground, and it's very good for us. Every once in a while, there can be a big blast of gamma rays or X-rays from something within our own galaxy. They're not gamma ray bursts, they're not that strong, but there are these other objects out there called soft gamma repeaters that are basically a big explosion of gamma rays from the surface of a star that just had a starquake. So it isn't blowing up entirely, it's just like a starquake on the surface. And there have been a couple of these that have been seen since Swift and Fermi were launched. One of them in particular happened just a couple months after Swift was launched in December of 2004. And it was 15,000 light years away. The gamma rays came to the Earth, they hit the Earth's atmosphere. They put so much pressure on the Earth's atmosphere that it squished the atmosphere down and made it be like a daytime atmosphere instead of the nighttime atmosphere, because they hit the atmosphere on the side of the Earth that was not towards the sun. And I know that people here are old enough to remember AM radios and having them, and knowing that AM radios work a lot better at night than they do in the daytime, right? You could get radio stations from a lot farther away. That's because at night, the atmosphere on the dark side is puffed up, and the radio waves from the antenna go and bounce off the ionosphere, and then they can come down much further away. In the daytime, all of the radiation from the sun squeezes the atmosphere down, and so those radio waves can't go as far. And so this neutron star, this pulsar, that was 15,000 light years away, was able to actually change the nighttime atmosphere into the daytime atmosphere. And it lasted for 45 minutes until the atmosphere recovered. That had never been seen before. So sometimes, these things can actually affect us on Earth. Not as much as a solar flare, for example, that can, wipe out cellular communications for a while. But it's still, I was just astounded that something that was that far away could actually affect the atmosphere of our home planet. Okay.
All that energy is being converted into, all that mass is being converted into energy. And you're seeing it pointed at us. What you're interested in and what you're so excited about. How much of a mass is being converted, and how efficient of that mass is being converted to that much universe? Is it 100% conversion of mass energy, or do you know, or is there?
Okay, so the question is, how much of the star, when it blows up, how much of the star's energy or the star's mass is being converted into the energy in the jet? And the answer is about 10%. Okay, so the other 90% is coming out just in the general explosion of the star and in the creation of a lot of particles called neutrinos, which carry away a lot of the energy, but not a lot of the mass.
Question right here, and please don't forget to hold the microphone right up so we can all hear.
This is something to do with particle physics and the symmetry and the opposite particles and things like that. I can't understand how they can measure something that occurs so instantaneously, and they can not only measure it in like that, and then determine the accuracy to some incredible assurance, you know. Can you explain how they do measure such instantaneous events that occur in particle physics?
Have you ever seen a picture of a big particle physics detector? The things are way bigger than this room. There are many, many layers of detectors, and all of those layers of detectors have electronic readouts and computers attached to them. And so every event, every time you get one of these conversions, sort of like the conversion I showed you in the Fermi Large Area Telescope, where the photon turned into an electron and a positron pair, except in the particle accelerators, they're much more complicated conversions than that. Every time they get one of those conversions, they get a huge amount of data, because there are all these detectors that track the particles, the paths of these particles. In fact, the Fermi Large Area Telescope is actually based on particle physics technology. Okay, so those trackers that I showed you, which, you know, are about that big, are just a crude, cheaper, lighter weight version of these monstrous particle physics detectors that surround the interaction point in the particle colliding beams. So they have beams of particles that are colliding around. The particles are accelerated to near the speed of light. They smash the particles together, and it makes a lot of energy. And then you get the pure energy. You get mass turns into energy. The energy turns back into mass. The mass that comes out is not the same as the mass of the same thing, of the things that they collided together. And every once in a while, it makes some really weird particles. And that's how they found the Higgs boson. But the way they find them, well, they don't find them that quickly because they have to comb through all this data, right? Just tons and tons of data with supercomputers for, you know, many thousands of hours. And then they see these rare interactions, and then they figure out what the particles were. And that's how they found the Higgs boson. 2 different experiments, but they're each tremendously huge detectors. I mean, they're bigger than this room.
Question over here.
Two-part question, if I may. Are there any stars which are not part of galaxies? And second of all, if you have a gamma ray burst occurring with an extremely large object on the lateral as a satellite to an existing black hole, will it take over the central point of the galaxy?
Okay, now I see if I can remember the first question. Okay, are there any stars that are not parts of galaxies? Not that we can see, because we can only see things that are far away if there's enough stars in one place to make a galaxy that shines. And we don't see any stars nearby that aren't part of our own galaxy. So if there was a star out there and it was all by itself, you wouldn't be able to see it because it would be too dim. So, right, unless the thing then explodes. And so you can see an explosion without seeing the underlying galaxy. That happens quite often. The galaxies are just too faint. You can see something explode. If you're lucky, the leftover gas will glow for a while and you'll be able to see something nearby, but that doesn't always happen. And if the gamma ray burst makes a black hole, it makes a small size black hole because it was a star. So even these big stars that have blown up, the core that collapses down to make the black hole that's born when the gamma ray burst happens, that's a black hole that is probably 15 times the mass of our sun, 1.5. Okay, that cannot at all compete with the black holes that are in the centers of the galaxies that are millions to billions of times the mass of the sun. So those black holes that are in the centers of the galaxies, they didn't come from blowing up stars. They were born when the galaxies were born. They were created when a big bunch of gas got together and made the galaxy. And so that's been another long-standing area of research. Which came first, the black hole or the galaxy that has the, you know, that did the black hole get created and then the galaxy grew up around it, or did you have this big galaxy form and then the stuff in the middle collapsed down and made the black hole? And so people have been doing all sorts of models called galaxy evolution models where they try to figure that out. And then all this new data came along and showed that there seems to be almost a direct correlation between the size of the black hole in the center of the galaxy and the size of the galaxy. So the bigger galaxies have the heavier black holes in the center. And so it does look like they were actually both formed at the same time, and they grew up together. So no chicken and no egg, they just were.
I understood that we see the bright spot when the accretion disk is, and the plume is directed directly at us. Is there a factor which directs them toward us, or would they be random, and therefore we are seeing 1/360th times the 360th power of the numbers of black holes that are possibly in existence?
It is the angle at which the jet makes to the observer is totally random on the sky. The opening angle of the black hole jets is between 5 and 10 degrees. So we see, 1/36th of all the black holes that are out there if they're sort of randomly distributed. Yeah, in one plane, and then, the other. So, there's really quite a lot of black holes out there. It's still sort of amazing that so many of them are making gamma rays and that are aimed at us. That was really quite a surprise. One of the bigger discoveries that Fermi made was the ubiquity of these black holes that are out there.
I noticed that in all of your discussion, you stayed with upper spectra satellites. I'm kind of fond of the WISE mission, the infrared program.
An excellent mission, but they've never given me any money, so I didn't talk about it. I have very good friends at Berkeley, however, who have been funded by that one and who work on that.
Yeah, that's quite a wonderful mission, actually.
It is, I agree.
Second part is the new James Webb that will replace Hubble. Will that have a package for you and your program?
I don't work on the James Webb Space Telescope either. That is all being done by the people that did Hubble. So the James Webb Space Telescope is actually an infrared telescope that is going to replace Hubble, which is basically a visible light telescope, at some future point if we don't run out of money first. And so it is now, I think, going to be launched in 2018, 19, something like that. It's been slipping into the future at the rate of 1 year per year pretty much for a while. So I think now I've been reading some pretty good results about the detectors are being finished and the mirrors are being finished. So I'm getting a little more optimistic that it will be launched maybe even before I retire. But I don't personally work on that. I've always been X-rays and gamma rays. I'm a scientific co-investigator on all of the satellites that I've been working on. And so that has always been my science, black holes and neutron stars. And I wrote many papers about observations of black holes and neutron stars that were scientific research papers before I got into the scientific education and public outreach business 15 years ago. So those are the missions that I'm the closest to, and that's why they want me to do their outreach and have given me the money.
Question over here.
Your description of the burst of gamma rays that compressed the night side atmosphere sounded most interesting and begs the question, did anybody speculate what would happen if that blast came on the side that was already being compressed by the sun?
It would have been harder to measure because it's hard to compete with the sun when the sun is on that side. And so I don't think it would have had quite as dramatic of an effect. But people have done some calculations of that, and I think one of the other super flares that occurred actually happened on the daytime side, and they saw a little bit of an effect, but nothing quite so dramatic. They're radioionospheric scientists that actually spend a lot of time measuring where the ionosphere is at any given point with these very long wavelength radio waves, and they're the ones that actually did the measurements of the nighttime ionosphere and saw the thing move, and then you could see it recover slowly after, as it recovered from being blasted.
Would you please tell us in a minute and a half what you've been talking about for the last hour?
Okay, well, some people seem to have gotten it. Sorry I didn't explain it properly for you. Where to start? Okay, I've been talking about seeing the most energetic forms of light from some of the most exotic and extreme objects in the universe. I probably should have given a better definition of a black hole. I guess I sort of assumed that people at least had heard of black holes, otherwise they wouldn't have come to the talk. I apologize. Black holes are regions in space where the gravity is so extreme that light cannot escape once you get inside the event horizon. And so they're popular in science fiction, but they are not just science fiction. But when I first started working in this field, back in the 70s, before I went to graduate school, there was really only one object that people had identified as a potential black hole. And people did not know that there were really, really big black holes in the centers of pretty much every galaxy. So all of the information about the existence of black holes and the proof for the existence of black holes of all of these various sizes, the small ones that are made when the stars blow up and the really big ones that sit in the centers of galaxies, that's all come about just in the time that I've had a scientific research career. Because the first black hole was really only identified in 1972. Okay, and so our view of the universe as, a place where we have galaxies, we have stars, has really fundamentally changed because we now know that black holes have been there all along. They're responsible for making the galaxies that we see. They're responsible for shaping the galaxies that we see. They affect the evolution of the stars that are in the galaxies that we see, and those stars, some of them have planets around them, and there's life on at least one of those planets. So it isn't totally practical. You can't go harness a black hole and use it to power your car. But gravity is the most, it's the most far-reaching force in the universe. It's shaped everything that we see when we look in the night sky. And it's certainly very important to us human beings living here on Earth. I hope that helped a little bit.
Can I ask a couple of questions? When you talk about detecting these particles far away, how many photons are we talking about, say, per second, per minute? And the second question is, since you don't have a model that tells how much intensity should be coming from these sources, how do you know how far away they are?
We know how far away they are because we can look at the sources with other wavelengths of light that we can use to measure the redshift, which I know that you know what that means. Okay, so the Doppler shift is, or the red shift and blue shift is this change in the frequency of light or sound when you're moving towards or away from something. You've all heard it when a siren goes by and it sounds high-pitched, and then it passes you and it sounds lower-pitched when it's moving away from you. Since everything in the universe is expanding, all of the light in the universe is shifted to the lower energies, so we call that redshift, because red is the lower energy of the visible light spectrum. So we look at the galaxy where the gamma ray burst happened, or the galaxy where the black hole is, and we measure its redshift, and we can tell how far away in the universe it is. So that's the answer to that question. As to the answer to the question of how many photons we actually get from one of these things, the brightest gamma ray bursts are about 1/1,000,000th of a photon per square centimeter per second. Not 1 million, 1/1,000,000th, 10 to the minus 6. So you need to have a lot of square centimeters to be able to catch enough gamma rays to actually make those maps and plots of the gamma ray bursts that I showed you.
Are there any other questions?
We got some more on this side of the room.
For many of us lay people who don't understand most of what you said,
how long is the length of our solar system going to exist? Do we have any projections? How long will what we have exist?
Our sun is going to last for about 5 billion more years before it runs out of fuel in its core and turns into a red giant and swallows up the Earth. So nothing to worry about, really. I mean, 5 billion years is quite a long time.
Is there any way to shine any light on dark matter?
Actually, Fermi has been searching for evidence of dark matter near the center of our galaxy, around other galaxies, and hasn't found anything definitive yet. So, okay, so what dark matter is, since this was not my Fermi talk and I didn't talk about dark matter. Dark matter is matter that neither emits light or absorbs light. And we know it's there because it interacts gravitationally only. So we can tell that there's a lot of dark matter in our galaxy, but we haven't been able to tell what exactly it is. Is it some kind of weird elementary particle that they haven't found in the particle accelerators yet? And believe me, they're looking. Or is it something entirely different? We know that 80% of the matter in the entire universe is the so-called dark matter. Only 20% of it actually interacts with light, or emits light, or absorbs light. And so Fermi has spent a long time looking for particle dark matter. And the way it is doing it goes back to that whole E equals mc squared thing again. So remember when we had the gamma ray and it turned into the electron and the positron? So those particles have a certain mass. It's actually 511,000 electron volts each. And so the gamma ray that made them is 2 times 511 plus a little bit extra if you then give them energy to keep moving. And so you can see the reverse of that process happen. You can see an electron and a positron get together and make a gamma ray that has the energy of 511,000 electron volts. And that's called the positron-electron annihilation line. And so you can see that. You can look at the center of our galaxy and you can see that process, the positrons and the electrons, the mass turning back into energy and coming out of that specific energy. You can see that from happening in the center of our galaxy. Now what they're looking for is a dark matter particle annihilating with the dark matter antiparticle and making a line in gamma rays at much higher energies. So that's what Fermi's been searching for when I say that they've been looking for dark matter. They're looking for the evidence of dark matter annihilating with another dark matter particle and making a specific gamma ray energy that would stand out somewhere where there should be a lot of dark matter, like the center of our galaxy, because there's a lot of stuff there, or around some other dwarf galaxies. And they've looked in a whole bunch of places, but so far, nothing definitive.
One more question.
Just sort of following up on that, that implies that even though they know practically nothing about dark matter, they have a model of what dark matter is. Like it's small particles. I mean, what occurs to me is why do they have some reason to think that it's not a distribution of black holes?
Okay, so where did the particle dark matter model come from? And that gets us back to our very first question the gentleman asked me about supersymmetry. So in the supersymmetric version of the standard model of particle physics, the lightest stable supersymmetric particle is sometimes called a WIMP, weakly interacting massive particle. And WIMPs are their own antiparticles. And so if you like supersymmetry as your model of particle physics, then you would really like WIMPs, and you would believe that WIMPs have antiparticles that are also WIMPs, and they will self-annihilate, and the energy will come out in the gamma rays. So that's what motivates the search. Why can't they be a bunch of small black holes? People have actually done experiments looking to find out if it could be a bunch of small black holes, or a bunch of rocks, or a bunch of Jupiters, or a bunch of other things that we might not be able to detect very well. And all of those experiments have failed. Of course, the WIMP experiment hasn't succeeded yet either, but it also hasn't been ruled out. Okay, but the machos, which are the opposite of WIMPs, the massive astrophysical contact halo objects, which would be the black holes and the planets and the rocks and the Jupiters, those models have been pretty well ruled out by people looking for them in the halo of our galaxy. So, no machos, but there's still a chance we could have some WIMPs out there.
Well, Professor Cominsky, thank you so much for a wonderful talk.